Let's talk about the formation of acetals. Now, acetal formation derives from a carbonyl substrate, and it's an acid-catalyzed reaction, resulting in a hemiacetal intermediate and then a full acetal after, I think it's about 6 steps for the mechanism. So here's the general overview of the reaction. If we have a general carbonyl structure, where I just label these alkyl groups R1 or R2, after a number of steps in what is a reversible reaction in aqueous acid, we form the hemiacetal, which looks like this, where instead of the carbonyl here, we have one OH group, but then we have an ether group, and I'll write that as OR3. Essentially, these are just alkyl groups. So on top of acid, we need an alcohol, right? So the general structure for that alcohol is R3OH. And after that, another iteration with a nucleophilic attack involving this same alcohol, we can form the full acetal, which looks something like this. R1 and R2 don't change. Consider that the backbone. But then, instead of this OH, we just have 2 of these ether groups coming off of this central carbon. This is the general overview of the reaction. We're going from an sp2 system to an sp3 system, but we do have a hemiacetal intermediate where we have one ether portion and one OH portion. Now, monosaccharides in their cyclic form are hemiacetals, and we see that from their structure. If we here, as you can see, one OH, one ether portion, here's the OH, here's that ether portion. So in its cyclic form, alpha D-glucose is a hemiacetal, and when it polymerizes with other sugar molecules to form starch, to form glycogen, those glycosidic bonds result in what is an acetal bond through the mechanism involving something a little different, but the same functional groups. So here we're given benzaldehyde, we have missing reagents, and we're asked to form benzaldehyde dimethylacetal. It's this compound here. So the first thing we should realize is that we have this diether moiety here with methyl groups coming off. That means this must have originated from methanol, which must be included in our reagents list. So the way we can write this is show that we have acid in water and we have methanol. Like with hydrate formation, we need to somehow increase the electrophilicity of the carbonyl carbon, which is inherently not very electrophilic in this case here, and in most cases when we have weak nucleophiles like methanol. So in acidic solution, the oxygen on the carbonyl becomes protonated, and thus it soups up the reactivity of the carbonyl, making it more susceptible to any incoming nucleophile, including weak ones. So that's what happens in the first step. We are activating the carbonyl. So we can draw benzaldehyde in a more abbreviated form like this. And what happens is we use our generic acid, H3O+, and in a typical nucleophile to electrophile interaction, the carbonyl oxygen acquires the proton, and those electrons go back to the water oxygen. What we form is our protonated benzaldehyde. Now this protonated form has a resonance structure where this positive charge can delocalize or spread itself over a larger area, which means there's greater stability. So what happens here is that by the movement of this pi bond, like so, the oxygen acquires an extra lone pair, but then the positive charge is shifted over to the carbonyl carbon. So when we do resonance structures like this, it's not that the molecule is in this form at one time and this form at another time. It's not resonance form 1 or 2 at any given point. What resonance tries to explain is the behavior of this compound, which means this charge is delocalized or spread over a larger area, which confers more stability. So really it's trying to explain that this positive charge exists not in this concentrated area or this. It exists in this entire area right here where this charge can delocalize. We can now carry out the first nucleophilic attack to form the hemiacetal. This structure, the positive charge is on the oxygen. We then bring in methanol, which can be abbreviated like this. The methanol comes in, attacks this carbonyl carbon, which is now even more electrophilic to this weak nucleophile. That sends the electrons onto this oxygen here, and that forms our second intermediate. So electrons flow to the carbonyl carbon like this. This pi bond breaks, and we have a change in hybridization where we have a neutral OH, our protonated form of the methanol attached to the carbonyl carbon, and here's our hydrogen like that. So we're almost at our first tetrahedral intermediate, which is our hemiacetal. All we need to do is get rid of this hydrogen right here. And what we can do is we take this, we use our conjugate base in what is an acidic solution. We could also use methanol, which is, and use that to deprotonate this hydrogen right here. So electrons flow from the water to the proton. It acquires it. These electrons go back to that methoxy oxygen, and we form the hemiacetal. Right here, we have one hydroxyl and one ether. And in the process, we've regenerated our acid. So we have H3O plus regenerated. So the question is, now how do we go from the hemiacetal to the full acetal, where we don't have this OH group and we just have another methoxy? One clue is that we've regenerated acid here, which can now act as a proton donor and donate it back to this hemiacetal. Now where's the proton going to go? Well, we have two potential targets. If the proton goes onto the methoxy oxygen, we come right back to this structure here, the protonated methoxy, which was the result of nucleophilic attack. If you protonate this group, it becomes a good leaving group, and it could jump off the compound and form methanol right here again. So that is a possibility. That's why this is reversible. But it turns out to form the acetal, this oxygen here must be protonated to form water. And water is a good leaving group, which can then be expelled from here, and another methanol can come in and attack. So in the hydroxyl is involved, I expand it out, I draw in all the bonds. Here is H3O plus, we draw in all the bonds, lone pair and charge. And because it's protonation, the hydroxyl oxygen functions as the nucleophile for oxygen. Another water molecule in the process, and our protonated hemiacetal. So you'll notice that water is formed in a lot of these activation or protonation steps. A distillation column can be set up such that you remove water. So you're adding stress to your equilibrium by removing a product. So that means this forward reaction here is really favored then if you start to remove one of the products. So that's one way to control the yield. Water is a good leaving group, can be expelled from the compound, and another methanol can come in and attack. What happens then is we form another water molecule, and now we are one step away from forming the acetal. So on one side, finally, all we do is remove this proton, send the electrons back to this oxygen, and what is going to carry out that work? Well, we have water, we can use that as the base. Theoretically, we could use methanol as the base here, the mild base, or the mild enough base to remove this proton. But for simplicity, I'll use water. And what is the final step? Deprotonation. We have regenerated our acid, which just goes to show that this is an acid-catalyzed reaction.